Okay, so let us start for today with rapid prototyping. For those of you who don't know me, my name is Martin Novák. I'm coming from Department of Instrumentation and Control Engineering, and I will have this subject with you. You can write me an email if you need it. As far as for the study materials, you can access them in Moodle. So please check if you can actually see the study materials and if you can get into the class. The code of this subject is shown here, and I will also show you the Moodle site. How does it look like? So here is the class in Moodle, and you should be able to get into the class. If not, then let me know either in the chat window or by email to to find some solution. It should be automatically synchronized with COS. So if you are registered for the class, you should have access to this materials. Here you can find the overview, what we will be doing in this class. First of all, take a look on the name. It's a rapid prototyping of hardware and software. So to avoid any confusion, we will not be talking about 3D printing, but we will be talking about creating software, especially for control systems that you can do in MATLAB. The schedule is shown here in this table. For the first 2 weeks, we will be talking about something that's called MATLAB embedded coding. I will be talking about it today and next week. Then we'll go into Simulink, and we'll focus on Simulink real time. Again, you'll see soon what that means. And then I see here I have some error here in the table. Then I will give you about 3 weeks to complete a project. So I will assign you a task, and with the help of the knowledge that we will learn in the first. Now I see I'm missing one lecture here actually in my table, and there should be four lectures in the beginning. So from week 5 to week 7 we will do the project, and then we'll have also another lecture. So this will be your work, and I will guide you how to complete it if you have some trouble. Then we will have 1 or 2 more lectures, let's say more theoretical, and then you will do project number 2. On the last week you will submit me the project number 2, and you will present me and to the others what are your results. Now, in order to finish this subject, you need to submit me project number 1, project number 2, and do the presentation. So for today, I will have, let's say, a little bit longer talk, and we will be talking about the basics of such rapid prototyping. Now, in my class, I will assume that you know how to work with MATLAB. If some of you know how to do it, some don't. I know that in parallel, most of you should have the topic Mathematics and Simulation Models with Professor Vyhlídal. So here you will use MATLAB as well. And at the same time, you should have also the class Embedded Systems with Mr. Hiski. So here in his class, you will use the same hardware as we will use here in rapid prototyping. Now, if you do not know how to work with MATLAB, then I highly suggest you that you start looking on the tutorials that you find on the internet and learn how to work with MATLAB. You will need at least some basic knowledge how to do it. The next thing that you will need is to understand a little bit C code. So if you already have some experience in programming, then this will be quite useful. Again, this class will not be really about C programming, but we will take use of C code to see what we will produce in MATLAB. So again, if you do not know anything about coding in C, then I highly suggest you that you start learning. In this subject, we will learn how to make quickly some prototyping of a control algorithm. I will see that here control algorithm will not be talking only about control algorithms, but we will be talking about algorithms in general. But I will focus mostly on control algorithms. So the next thing that you should understand is also that for at least PID controllers. And what we will do is that we will look first in simulation how we can control some system. We will do the simulation in MATLAB or in Simulink. And then we will compile this simulation of the control system to a real hardware. So after you pass this subject and together with other topics that are running right now, you should be able to do the following. You should be able to implement the plant model in simulation on a computer in Simulink. You should be able to work with the control algorithm also in simulation, and then you will be able to deploy this algorithm directly to a hardware system that can control the plant. And the plant can be either the real plant, like the real device, the real system, or it could be also the simulated system that is running on a computer. Why is it useful? Well, this approach is used in many areas. You can find it in automotive. Here, a typical example is the development of controller units for the combustion engine. So the way it works in the company is that they develop a mathematical model of the combustion engine. This model runs in simulation, for example in Simulink, and then they design the control algorithm also in simulation. And here they can test if the algorithm is suitable, if it is fast enough, if it has the desired response, and so on. And only when this is finished, then they will deploy that on real hardware, and they will verify that this works with the real hardware. Another area where this approach is used quite frequently is aerospace. So for example, if you design an autopilot, you obviously cannot test it directly on the airplane. So you design everything in simulation. You test in simulation if it works. Then you take your control algorithm, implement that on real hardware. You test that with a model of your system, so with the model of your airplane, and only when this works you can start testing on the real airplane. So there are many steps that you need to do. Another example, so my last example would be the robotics. So here, imagine that, for example, you're designing a robot that will weld some frame for the car. And again, you can start with simulation of the robot. You can then implement that on hardware, and only when this is finished, you can start testing on the real device. So what we will do is that we will go through all the steps that you require for this process. Now I understand that it will be quite complicated, because at the same time you will be learning in other subjects what is required. So what you will definitely require is the knowledge about control systems and about how to model the control system and the plant in simulation. So as I have already told you, this is done in another subject with Professor Vidal. I believe the subject's name is Mathematics and Simulation Models. So we will here assume that you are able to create a mathematical model if you have the differential equations. Then when we have this simulation finished, what we will do is that we will create a C code, and this C code will be compiled into the control system. Again, we will not focus here on coding in C, but you should at least understand the basics of C, because sometimes it will be necessary to modify a little bit the C code that you have in order to run it on the hardware. So you need some basic knowledge. You need to know what is the variable, what is a function, and you at least you will need to read the code that MATLAB has generated. It will be the same for all the topics that you see here, regardless if we use MATLAB or Simulink. In both cases, the tool will produce C code, and then this C code will be compiled. I will tell you more details about the project number 2 and the project number 1 in a few weeks. I already have the assignments, but I need to translate them into English. But in general, the project number 1 will be about creating the plant model in Simulink real time and run it in real time on a computer. And then project number 2 will be to create the plant model, but for a different plant, and also to create the control system and then implement it on the real hardware and see if it is working, what are the limitations, what is the accuracy, and so on. Now, from project number 1, I only expect you to show me the result. So I will not request any report, any written report, but I will request from you the model that you have created. On the other hand, from project number 2, you will need to create a report about how have you created the model and what are the results. And I will also require the presentation that you will do on week number 13. Now this schedule is for the ideal case that we will really have the lab classes in school. So far, for the time being, we can do it online because we will be working with MATLAB and Simulink, and I can show those tools online. But then we will come to a point where we will require the real hardware. And I really hope that the school will reopen, let's say in, I don't know, 3 weeks, 4 weeks, maybe, who knows, and that we can meet in person in the lab. Now I see that we have more attendance here. We have 5 students currently. And I would like to ask you if this time that we have is convenient, or if we can shift the class to another day. My proposal is the following. And again, I don't know if you have time at this time, but I have the same class like we have right now with the Czech group on Monday. And I already asked them if it's okay for them that we merge the group and we have all the classes in English. And they seem to be okay with that. So my question to you now is if you could have this class also on Monday, starting
For
from 11:30.
me, I cannot. I have to studies like from 9 until 1:15, and
Uh-huh.
from 2 until like 5:30. Yeah.
Okay.
So it's gonna be full day for me on Monday.
So it's not
Mm-hmm.
possible. Okay.
Mm-hmm.
Uh, Fine. So then there's no option how to do it. Okay, no problem. So we'll keep the
Okay.
classes at this time on Wednesday from 2:15.
Okay.
Okay, good. So what will you need? You will need software, and you can get it from the download site of the university. So if you go to download.cvut.cz, you have to download MATLAB. I have already written you an email that you should install it for today. So I hope you have received that. And here you should install the campus-wide MATLAB license. And as we will all need the same version, then I suggest that you use version 2020B. It's not that critical if you, for example, have 2020A or something else. The only reason for this is that if you have some trouble with running the code or with the MATLAB, if I have the same version, I can try it and I can find some solution. Now, if you have a different version, then this is not possible. So please be so kind and install this version of MATLAB. You will need at least those 3 toolboxes: MATLAB Embedded Coder, MATLAB Real-Time, Simulink Real-Time, and Simulink Coder. As you probably know, there are many toolboxes in MATLAB. You can also install them all. It's up to you if you need them or if you have enough space on the hard drive. As far as for the hardware, I will use this board. It's called Nucleo, and the microprocessor is named STM32F767. And now here I see there is again a mistake. There should be ZI, like that. So when we will be in the lab, we will be working with this development board. You will use the same development board also with Mr. Hiski on his classes of embedded system. Now let me ask you, is here someone who does not have this embedded system class? So all of you have embedded systems.
Yes, I do have it.
Okay,
Me too.
okay, great,
I don't have it also.
great. So we have discussed with Mr. Hiski that well, he told me that he asked you like maybe 2 hours ago if you can actually get this device.
Yes,
Is
true.
it-
He did ask us to get this device, and we agreed on maybe some, like we can order it through him.
Hmm. Okay. I have already sent him the link where it's possible to obtain. It's something like 550 Czech crowns,
Okay.
so it's not very expensive. Uh, so he will send you this link. I think the best option is if you write him uh, and we will make a list and then we will order it at once so that we don't need to pay shipping multiple times, and then we'll meet somewhere in front of the school and he will give it to you. Okay,
No problem.
Okay.
Yes.
good. So this board will be required from well, we will already use it next week, so it's best if you can write him uh, that you want it or that you need it, and we will order it quickly. Typically, it's here within the next day. So, if for example I would order it today until maybe 3 p.m., I would have it tomorrow. So, it's very fast, but we will need it next week on Thursday. In case we will not obtain it, I will in time I will find some other solution. Maybe we'll just do some simulation, but in about, let's say, at least in 2 weeks we'll definitely need this board. Okay, so now let's take a look on the different levels that we will discuss during this class. And by different levels, I mean different levels of simulation or reality. Now, what we can do is we can use an approach that's called model in a loop. This approach you probably know from, let's say, simulation topics like maybe automatic control that you had in previous semesters. The approach works with a controller, but this controller is not a real device, but note that this is a model, and it means that we do not run the real system, but that we use this model. And by model here, I mean the mathematical model. We do the same thing here also with the plant. So here know that this is a model as well of the plant, and by plant here we mean the actual control system. So the plant, that could be a model of I don't know, of a thermal controller. It could be a model of the combustion engine, or it could be a model of an airplane. Now in this approach, the model in the loop, we run this in simulation. And what we can do is that we can record the results for future comparison. So now we can take this as a reference, and we can verify if my results in the next stages will be similar to the model in the loop. Now, why do we do this? If you run it in a model, you are basically running with a very high accuracy of the calculations of the numbers. You don't have any disturbance from electromagnetic interference. You don't have any disturbance from the inputs with noise and so on. So here this is like the ideal state, and we will compare all the others to this ideal state. On the other hand, you need to remember that the plant here, this is only a model. So it may not include all the effects that we have in reality. For example, we typically model the plant and the controller as linear systems in many cases. And in reality, the system might be non-linear. So then the real plant, which is, let me just quickly repair this. So the real plant that we have here may behave a little bit differently. So now this typically is a first stage. We try everything in simulation. Now, of course, if you are doing a control of a simple system, then you will most likely not go through all those 4 stages. If you are doing a controller system for an aquarium at home, you will definitely not model that in simulation, and you will not model the controller. You will directly jump into this part where you have a real controller in hardware and where you have a real plant. This approach is, however, useful for more complicated systems, where you need to make sure that it really works, that you need to have some records how well is your controller performing. And during this class, we'll work with all 4 approaches. So we will start today with the model in a loop approach, and we'll work with this maybe for the following 2-3 classes, and you will see that it will slowly change into the software in the loop and processor in the loop, and then at the end, about half of the semester, we will see hardware in the loop system, and you will understand what it means and how can I use it. So this is the first stage. The second stage is called software in loop. Now note that there is a difference. Here the plant is still a model, so we are still running the simulation that is based on some differential equations, but here this controller is already done in C code. Now here I'm showing C code as an example, but nothing prevents you to use any other language. So it can be C++, it can be Python, it can be anything else that you can imagine. But here the point is that in the model in a loop system, we have the controller as a mathematical model. So this is based on equations, either on differential equations or algebraic equations. But here it is also implemented as some code in some programming language. Now, why can this be different? Now, in a C code or any other language, you typically need to define variables, and the variables that you can use need some ranges. So we will find that we will have a more limited accuracy here in the C code. We will also have some delay in the calculation, because here in the model it does not run in real time, so we don't really care how long does the calculation take. But here, if you run it in C code, then this needs already some timing. So what might happen is that you find out at this stage that your controller algorithm was working well in the model, but it's not working at all in the C code, because, for example, it can be too slow, or it will not have enough accuracy in the numbers. And then you need to go back in the model and you need to design a different algorithm so that you can implement it actually in C as a software. Now what we do is to compare the results that we have in this stage with the previous one. So we, for example, make a transient response. We see what is the reaction of the plant and of the control system, and at the end we see what are the differences. Now typically what happens here is that you find lower accuracy and maybe some problems with speed. Now the third stage is called processor in a loop. Now note that there is only one slight difference. Now here in this processor in the loop, note that here we have the real hardware. So here the C code was running on a computer, and it could be the same computer like where we have the plant model. But here we already have some real hardware. So this hardware could be, for example, this board. And with the help of some real physical signals that you can find on those terminals, it is communicating with the plant model. Now the main difference between processor in the loop and here hardware in the loop is that the processor in the loop does not need to run in real time. And I will explain in a few minutes what this means. So note here that this runs on hardware. And as we have the hardware controller already, which might be the board, we can connect it to the computer and we can run it with a plant model that is in simulation. Or what we can do, we can already connect the plant and we can run it with the real plant. So here you can see that in reality this is our result. This is what we want as the final product. We have a controller that is implemented in the hardware, and here it's running with the real plant. So here we will have some communication signals. It could be sensors that we have in the plant. It could be controlled signals that are controlling the motor. It could be a signal that is switching relays and so on. Now if you are at this stage, it does not have to be real signals. So at this stage we will have the same signals because it's the same plant. But as this plant runs in a model, we may exchange the data also through USB or through Ethernet or through some serial connection. Those are just few examples. In case of a real plant, it might be similar, but it might be also some analog signals. So some voltage or some current that is being transferred between the plant in reality and between the controller. Now the board that we will use allows us to do both. So we can connect real signals to those terminals that we have here, and some signals can be digital signals and some signals can be analog signals. We can also send the data through the Ethernet or through USB, or we could send it as a serial line, for example. We will see few examples during the class. We will in most cases use the real hardware signals if we will be in the lab, and if not, we will most likely just send some message to the computer saying what is the actual value of the variable, and we will see it on screen. Now if we will be working in a lab, we have equipment that allows us to run this plant model on a PC, and we have a different hardware devices that can output and input the signals. So if we will be working in the lab, which I really hope we will soon, maybe in 1 month, but who knows, then we'll work with the model of the plant that runs on a PC. Now, if the labs will still be closed, what we will do, or at least what I would like to do, is that you will use this card, and I will give you additional cabling that should allow you to connect this card through the speaker and microphone inputs and outputs on a PC, and you could run the model on your own computer. Now it should be possible in theory. So far I didn't have time to test it, so I will let you know, but I think it should work. So this is the stage that we should reach at the end of the semester. We will have the real hardware, and we will have the model, and here we will communicate with the real system. Now here there is a note that this does not need to run in real time. If it's called a processor in the loop, then it does not need to run in real time. So the plant model can run very slowly, and also the controller model can run very slowly. Ideally, we will use the approach that's called hardware in the loop. I say ideally because in some cases it's not possible to create it on the hardware that we have available. What does it mean real time? Imagine that you have a very slow system. You can have a system that represents a model of a temperature controller. You want to control a temperature in the room, and it's quite slow. You need to check the temperature every 5 minutes, for example. So every 5 minutes you read the temperature, you do some control algorithm. So here this will be your temperature, this will be the measured variable y. The controller will calculate what should it do, if it should turn on the heater or turn on the cooler, and then it will send the output signal to the plant. Now if this is a slow system, it's not difficult to do it in real time. In real time means that you can calculate the control algorithm fast enough. So it means that your controller is running very quickly, and that there is no significant delay between the reading of the variable that you're controlling and the output. Now in case of a slow thermal system, it's not difficult. If this plant requires a control algorithm to act every 5 minutes, then the controller in hardware has enough time to do it. So it's all about the ratio between the speed of the plant and between the speed of the controller. On the other hand, there are systems where this might be very difficult. For example, if this is an electrical system, you can control an electric motor, then this fast system may require a very fast reaction. So for example, here let's say that I need to control the plant every microsecond, so something like this. There are really systems that require this speed of control. So if this is the sampling rate, 1 microsecond of my system, then if I have a controller that has 100 let's say milliseconds reaction, then it would definitely not be suitable to control this plant. So if it should run in real time, now the delay that you create in the control algorithm should be much smaller than you have in the plant. So in our systems that we will study here, we will need to change the properties of the model. Now the models I have created for the project 1 and project 2, some of them are slow enough so we can control them correctly with the hardware that we have available. Some other systems represent devices that are very quick, and in this case we will need to change the settings of the system. We will make them deliberately slow, but then it will not correspond to the reality. It will still be the valid mathematical model, but it will not represent entirely the reality, because it will be, let's say, 100 times slower than the real system. So at the end of this class, the project number 2 that you will do will be about this. So you will first go step by step through all this approach. You will create the model of the plant. You will create the controller, first in simulation and then in the real hardware, and with real signals you will control the plant that runs as a model but in real time, and it runs on a PC. It could run also on the same board, but we will run it on a PC. So the final result will be this, a hardware in the loop approach. Now, how will this work? Today and next week we'll be talking about MATLAB. So we'll be talking about this part of the diagram. Now what we will do is that we will be able to produce the code in MATLAB. So here this will be our MATLAB code. Today we'll see some simple functions, and then we will run the tool that's called MATLAB Coder or MATLAB Embedded Coder. What is the difference? Now MATLAB Coder is a tool that allows you to produce C code or C++ code that runs on a PC. And we will do it today. Today we will produce a code that runs just on a PC. Now if we want to create a code for an embedded device, for a microprocessor like we have on our development board, then we will use an embedded coder. So this will use a different tool, but in MATLAB it will still be the same. We will just have to configure the compiler to use a specific platform that we need for our development board. In all cases, here we will produce C code. Now the coders in MATLAB and Simulink can also produce C++ code, but we will just use C code. At the end, this is like a byproduct, and we will watch this byproduct and we'll see how is it created. We will then run a compiler, and this compiler compiles the C code, which is a kind of universal code, and it will compile it to a specific hardware. And today we will do it for PC, so this will not be, well, it will be hardware, but it will be PC. It will not be the development board. But starting from next week and on, we will work with the hardware on the board. So this will be a different compiler, but the steps will be exactly the same like you will see today. And then in 2 weeks we will do the similar approach with Simulink. First of all, we will see in Simulink how we can actually create some model of a system. I think the most basic system that we will create will be that we will blink with an LED. And then by using Simulink Embedded Coder, we will run this code on the development board, and we'll see how does it run. Before we begin with some examples, let me talk just a little bit about what can it do. Now, the MATLAB Embedded Coder supports different standards that are used in the industry for safety devices. Now, obviously, you will not use the approach that we will learn for simple systems. But if you are designing an electronic control unit, that's this ECU, for a combustion engine, then you will need some level of verification. And you will need to prove that your code works first in simulation, what are the results, how well does it work, and then you just deploy that on hardware and you test it again. So those standards that you see allow the designer to fulfill the task of safety. Now there is one standard called AUTOSAR, and this is specifically a standard for automotive, and especially it's supposed to help with the design of open and standardized electronic control units. And the second standard is a more general. It's also supported by the embedded coder, and it's about safety related systems. So for example, if you're designing a programmable controller for an assembly line, for a robot, or for an airplane, for example, then again you need to make all those verifications, and you need to be able to prove how your software is working. Now obviously there are more standards that are supported by MATLAB. Now those ones are just the basic ones. The embedded coder supports many families of microprocessors. Today we will work with the Intel compiler, which is what we have in a PC. Even if it's AMD, for example, then it's Intel-based architecture. The board that we will use is from STM, so we will need also an additional compiler for those STM boards. And at the end of today, I will show you where you can actually get that. Now the MATLAB coder or embedded coder can generate basically three possible outputs. Now the first output will be the source code. So if for some reason you need just the source code, then you can take this byproduct and you can see it and you can use it as a library in your devices. The second possibility is that we have a dynamic or static library of some function. Now the difference is that if you have a source code, you may modify the source code. So you see directly what the developer has created, and you need to compile it and you can modify it. Now if you don't want to allow that, if for example you are giving your product, selling your product to someone else, you can create a library, and then the person who buys your product can use the functions that you have in the libraries, but he's not able to see the source code, so he's not able to see how you've done it, and he's not able to modify it. So it's also possible to create those libraries from MATLAB. And the last option, again here I see I have a should be C. The last option that we have in MATLAB is that we can create accelerated code for MATLAB that runs on a specific hardware. What this means is that we can create our algorithm and we can compile it, and then we can run the compiled function. Now you probably know that MATLAB is an interpreted language, so it's going line by line through the code and it's doing what you have in the line. This approach is very good if you want to debug your code, but in terms of speed it's much slower than if you have a compiled code. So what this is doing is that you compile your functions and then you are calling the already compiled functions for your specific platform. So today we will do this last approach, and we will also see what are the speed advantages. And at least in the case of my computer, the advantage was about between 50 and 100% increase in calculation speed. So it's quite significant. Okay, so do you have some questions so far?
All good.
Okay, if you have no questions, then what we will do now is that now it's a good time to launch MATLAB, and we will work in MATLAB. So right now I will show you some examples that we will do in MATLAB, and I hope that you will be able to do in your MATLAB as well. And then I will randomly select some students. They will show us their computer screens, and they will show us how the program is working in MATLAB. So try to work with me on the functions. Now what we will do is we will start with a very basic example. Now I will create a function, and this function will do some calculation. Now I have selected this result. So I will take variable A, variable B, I will multiply them together, and I will add 2. This is just a random function. I just want to show you here how everything works and how we can actually compile the code in MATLAB. So what we will do now is that we will write this function in MATLAB. I will just close all my scripts from the previous class. So now what we will do is this. Here what I have just done is that I have created a function. Now this function is called C, and here sorry, not C, but C is the return variable, and the function is called like that. That means operation 1, and here you have the input parameters. Now note that in MATLAB you don't need to specify the types of the variables unless you specify something else. This is a double, so it's using a floating point number, and the range is double. You will see that this will be quite different in C. In C, we will need to specify what is the data type for this variable and for variables A and B. Now this is a very simple function. Here we see that this is just a mathematical formula, and when this function is called, then it calculates the result and it will store that in the variable c, and then this will be returned to the function that has actually called this operation. I need to save it, so I will just save it in some end file, and I will use the ones that I already have here. Now we can try that manually. Here in my MATLAB, I can just clear everything, and I can assign some numbers. So let's say I will assign that a equals to, let's say, 10. I can assign that b equals to, let's say, 5. And now I can manually verify if this code works. So if I just copy it like that, then I know that this is 10 times 5, that's 50, plus 2, that's 52. So in C here I have 52. Here I have the variables that I have just created in MATLAB. So this is one file that we actually need. If someone has a problem, you need to react immediately. So if you're not able to do this, then let me know. What we now need to do is that we will create a higher level function that will call this function that we have just created. And it's a very simple procedure. Here, just write a single line in MATLAB. This is the name of the function, and those are the parameters. So let me just copy it back to MATLAB. I will create a new script and I will just copy it in there. So now what this is doing is that it's calling my function with parameters 2 and 3. And since I know that this is a times b, so 2 times 3 is 6, plus 2, which should be 8. So here if I call this function like that, I should get the answer 8. I can modify the parameters, so let's say I will use parameters 20 and 30, and now I can call it, and we see that the response is 602. Now we need to create this script in order to give the compiler sufficient instructions when we are compiling the code. Because what will happen now is that we will compile this function and we will see the C code, and we will see also the input types and the output types of the variables in the C code. So we need to save this as another file, and I have used this name, operation1 underscore test. And again, I've already done that, so I'll just overwrite what I've done in my previous attempt. So now we have those two files like that. And now it's time to run the compiler. You'll find it here in apps. So I hope that all of you have MATLAB installed with the toolboxes. And here we will run this MATLAB compiler. And you can see that if I hover above it, it's saying that it will generate C code or a max function. And we'll see in about half an hour what the max function means. So now let me run the coder. It starts the tool, and we will see a wizard that will allow us to configure the settings of the C code. Now, what can we do with that? We first have to give the function name that we actually want to compile. Now, right now, I have only one M file in my folder that I can compile. So this will be this operation1 M file. It's not the test file, but it's directly my function. So we will select this. Now you can see here that we have the function name. We can select where this project will be compiled. And here we can select if we want some numeric conversion or not. Now what does this mean? It means if I use no numeric conversion, you can see here that it will use the data types that are defined in MATLAB. And I told you that the default settings for MATLAB is double. So it will use doubles. Now this runs fine on a PC. But in many cases, if it's some embedded hardware, then you are limited in accuracy. And for example, the, let's say, simpler controllers might have only floating points, or they may have only fixed point numbers. So here you need to select what will be the conversion. For example, if you convert it to single precision, you will be using standard floats that are available in C. If you are limited with the hardware, then your CPU may not have the floating point unit inside, and you may need to convert it to fixed point. We will see also an example what is different here in terms of accuracy next week. So far we will select no conversion, but remember that here for the specific hardware devices you may be forced to select something else. Now the board that we will be using, the STM32 board, is a floating point controller, but it is only a single precision device, so it will use this single precision. If you use another device that does not have the support for floats, and you, in C at least, you still can use floats, but it may happen that your code will be very slow because it will not have any hardware acceleration. It needs to convert the floats into integers, make the operation, and then it will convert it back. So typically what happens is that if the programmer does not think about this, he will create a code that is very slow and may not be able to run at all with the hardware. So as a developer of embedded hardware, you always need to think in advance, what accuracy do I need, and if I really need to run everything in floats, or if I will run it in integers. On some hardware, the speed difference may be few orders of magnitude. So if you run it in floats, or if you run it in fixed point, there may be like 1,000 times speed difference. So far I will select none. Now I already have this project, so I will just overwrite it. It should not be the case for you. And now in the next window, we need to specify what is my test function. So I need to define my test script, which was this one, the underscore test. It's a good idea to name it with the same name and then some underscore and then the test. Then I see immediately that this test file belongs to my function. And the reason why we are doing this is that we want to define the input types. And you can either do it manually or you can do it automatically. Now actually what this was doing, if I pressed this button, is that it was running the script and it found out that it has two variables, a and b. That's here this variable, and that those two variables are floating point numbers with double precision. So here you can see that it found that it's double. I could modify it manually. For example, if I want to use single, or if I want to use signed integers or unsigned integers, I could redefine this result to something else. So standard in MATLAB is double, but for hardware you may need also those other types so that you work fast enough with your hardware. And those numbers here, this is the range. So now in my example, you can see here that this is just a number, it's a constant, and here it's a constant. So it's not a matrix or it's not a vector. What you can do here is, of course, you can redefine it. And we will see in about 10 minutes what will happen if we, for example, use a matrix as the input. So far so good. Does it work for all of you?
Yes.
Okay, great.
For me, it doesn't work for some reason.
For me also.
It doesn't work? So show me your
No.
MATLAB. Share the screen and show me the MATLAB.
Here you can see it.
Yes.
I think the problem is somewhere. I have the same code as you, so you can check it.
Okay. Function. I see what's the problem. You don't have the correct path to your M file. Now note on my screen, you have stored it somewhere else.
Yeah.
I will show you on my screen where you need to be. Note that now here I have this path in MATLAB, and I can see my functions over here. So this means that I am working in this folder. You have saved the file in a different folder, and you are not in the folder. So if you run it, it cannot find the correct script.
How can I change the path?
Well, like this, you can open it, and you can select a new folder where you actually want to work.
Okay.
Or you can just go through this structure, and you can double click on the folders, and you will change actually this path.
Okay.
Fine.
I also have problem.
Show me your screen.
Yes. This one.
Okay.
And if I do this, it says it doesn't find something.
How can I read it? I can't read Japanese.
So, yeah.
So I suggest you that you install MATLAB in English.
English, yes. Okay, I will do that.
I cannot help you with that.
Okay. So I will just skip it. Yes.
But maybe you have the same problem because it might be just the folders.
Okay. Thank you.
Fine. So let's go back to the MATLAB coder. Now we can advance in this compilation, and now what will happen is that we can check the code for any issues. But the point here is that it will run the test file, and it will see if there are some trouble in the code. One problem might be, for example, that it does know the function like you have. Another problem might be that there might be some overflow in the numbers. Now in MATLAB this will not happen, but in C it can happen. Another example is that some variables might not be defined, and so on. So now if we just hit this check for issues button, what it's basically doing is that it's running this test file. You will see it here that it will appear in the result, and it runs my file in background. So for example, if I will have some plots in the file, they will be happening in the background. Now here, this building max, we will use it in about maybe 15 minutes. So I will tell you then what this means. And also here, this result. Now you see that here in background, in this place, it has actually started my script. It has run the test file, and it's running the test file with the numbers that I have here. So in my example, I have numbers 2 and 3, and if I plug them in this equation, so 2 times 3 is 6 plus 2 is 8. So here I can see this in background, and I can see that this is okay. Now this code is very simple, so it did not detect any issues. If it did, then it's probably an error, for example, that it cannot find the path also. For more complicated program, it may give you some advices how you can actually improve the code. And one typical example is that in MATLAB you don't need to define the size of a variable. So if you make an array, so for example, if I would to define an array that's called, let's call that E, like this will be my array, and if I use the index variable, let's say like this, I will write to the first position of my array, and then if I do this, then I can write number of 20 to the second position. So now if I run this in MATLAB, what will happen is that this will define the variable, and it will assign the value. So now E equals to 10. And if I do the second line here, now what will happen is that I will have an array. So now you see that it automatically has created this as an array, and the first element is 10, the second element is 20. And by using those two lines in MATLAB, and first this was a single number, like only the number 10, but here it has automatically changed the size of the array to 2 by 1. And if I do, for example, this, let's say I want to write to position 10, and I will write value 80, and you see here that it will automatically fill all the other elements with zeros. Now if you have something like this in your code, it will give you a warning here in the issues, because you cannot do this in C. In C, you need to define in advance what is the size of your variable. So you need to think in advance if this will have 100 elements or if it will have 10 elements. So that's an example where this might give you the warning that it's not possible to do it like that in C. Anyway, for our code it's fine, so we can proceed with the build. And before we do the build, we need some configuration. So here we can find the compiler configuration. And we can adjust, or we can set many things in this compiler. Now I will go only through some of them. We can, here, this window, we can select where we want to compile it. You can see here that we can compile it to MATLAB. So MATLAB host computer, this is a PC that we are running right now. We can get also some packages for different platforms, and that's what we will do next time. So next time, in I think 2 weeks, we will need to install actually a support package for MATLAB for our board, and we will need to add it here, and we will need to select it in this selection. So right now we'll just select the host computer. We will also look in the more settings, and I will only go through some tabs here, and I will explain you what they are doing. So first of all, let me introduce here this one that's called saturate on integer overflow. Now what this is doing is that it adds some code in the C code that will check if you have overflow in your calculations, but overflow with integers. So so far we don't have integers, we have floats, so it will not be in our code. But if you will use integers in your coding in MATLAB, then this will add some additional lines of the code. Now why do we need this? If you are working with integers, it's relatively simple to create a number that does not fit into the range. Now integer is a number that does not have any decimal places, and it has only a limited range. For example, if we use a 16-bit integer number, then it is giving you the possibility to work with numbers only in range between minus 32,000 and something up to plus 32,000 and again something. And actually it's not, it's 32,756. And now imagine the following situation. You have one number, let's call number A, and you have A equals to 30,000. So let me go to MATLAB, and let's say that A equals to 30,000. And if then I will use B equals to 20,000. For example, like this, we know that the sum should be 50,000. But if I do this in integers, so for example, if I do this in float, A plus B, that's 50,000. But if I do this in integers, then it will overflow, because the range in integers is only 32,700, I don't know, 56, like this, 68. So this is the number that you can fit in integers. So if your data type is integer, what will happen is that it will overflow and you will get a completely wrong result. So here this will prevent that, and the price that you pay for this is that it will add an additional code to your C code that will prevent this overflow. And saturate means that it will stop the result here on this maximum number. So for example, if I would do this operation a plus b in integers, I know that it should be 50,000, but if it saturates, it will be 32,768. So this is a warning for you. If you are using integers, then you need to be aware that they may overflow. On the other hand, the operations with integers are native for the CPU, so they are very fast compared to floats. So that's this setting. Then we'll just take a look on the tab that's called Code Appearance. And here I will just explain this and this setting. So in here you can see that during the compiling we can actually add the MATLAB source code as a comment. So what will it do is that we will see the C code, and the comment will be the code that was used in MATLAB. So this is useful if you need to look back and you need to see if a little bit later maybe remember what C code have you created, and also it can allow you to orient yourself easier in the code, because you know that in MATLAB it was this line and in C it is this line. So I will check that in my compiler settings. And this second option allows me to convert the else if statement correctly into, not correctly, but let's say so that it's readable in C better. Now in MATLAB, if you have been working with MATLAB, then you know that we can use this if-else-if statement, and in C it does not exist. In C we have a switch case statement. So if it's possible, by checking this, it will use the switch case, which in C is easier to read than all the ifs and elses that we have in there. For the time being, we'll not need that. Okay, I think that's enough right now. So now just let's generate the code. So here I will press the generate button, and now it will take my C function. Now in background it will, see here, it's building the code, and in few seconds we should see the result. The result will be several files. We will have one file for my function. You see now that it has just appeared. This is the C file. We will have the main function, which is here. Right now we will not need that at all, but this would be the place where you write your own code, and you are just calling here this C code, this generated function. Now we can see here that in this code we have the commands from MATLAB. it's saying that this was this file, and on line 3 I had this code in C. So if I now go to my MATLAB here, here you can see that this really is on line 3, and this is exactly the same code. And you can see how it's written here. This is the name of the function, this is the type of the return parameter, and this is the definition and type of the input parameters. Now note that here we need to define the types of the variables. So in MATLAB it was not necessary. Here we have just A and B, but in case of C code you need to specify here what is the data type. So we have kept the double type here for all the variables. Now if my CPU on the embedded hardware does not support doubles, then this could give me an error, or it could be very slow because it needs to be translated into many commands in integers. So here this is where you can actually gain quite significant improvement by using less accurate calculations. And here we see the calculation. Here we see A, B plus 2, and now note that here we have 2.0, and if I go to MATLAB we have just 2. The reason is simple. If you want to write in C a number that is a float, you need to have this decimal comma here. So this is still 2, but it's telling the C compiler that this is not an integer 2, but that this is a float 2. Okay, so let's see what we can do with this code. Now let me modify my operation in MATLAB. I will just finish this tool, and now I will go back to my operation here. So what we will do is that now we will use the same function, but the input numbers will not be numbers, but it will be a matrix. So what we will now do is that we will create a matrix of random numbers, and in MATLAB we use the command rand, and I will generate a matrix that has a dimension of 3 times 4. So it has 3 rows and 4 columns. And now what I will do is that I will create a new test file, and here instead of the 2 I will create one random matrix with 3 times 4 dimension, and the other one will be also a random matrix, and it will be 4 by 4. And I know that my function is multiplying the two matrices together, so here I need to have this dimension to be the same like this one. And I will save this as test file number 2 for the same M file for the same operation. If I run it manually, the result will be a matrix. So this is the result. So here we see that I have used the same function. Here I did use different parameters. A and B is a matrix, C will be a matrix as well. The function is doing the same calculation, exactly the same. I did not change anything at all in my function. But here I am using the function with different parameters. So now let's see what will happen if we compile this and how it will change the code. So let's run it again. I will do again the same steps. So I will define the function names. So my function is the same, operation1. I will not use any conversion. Well, we can actually just convert it to single so that we see that it's really different. And now I need to define my test file. So here we have the test file. This is operation2, operation1, and test file number 2. I will define the input types, and now you can see that it's a matrix, double matrix, 3 by 4, and B is 4 by 4. So now what will happen is that the inputs will be doubles, but as I have converted the output will be a single. So let's run it again, and we will run the issues check. It will again run the code in background, and in this case it will not give me any suggestions because it's a simple code and there is nothing to improve. Okay, and now we'll just compile the code with the same setting like we had before. I will just generate the code, and what we will see is that this code will be completely different. Now remember that in the previous case we had just one line and we had a times b plus 2. But now, since this is a matrix, here we have matrix A, matrix B. Now you see that the code is much more complicated, and it's multiplying the matrices together. So this is called polymorphism. It means that the same code in MATLAB can lead to a different code in C. We have just seen that here this is a different code, and actually here this is the multiplication, and you can see that it runs in a 4 cycle. So you can see here that it's running from 0 to 3, and here so this is running through all columns, and here this 4 cycle runs from 0 to 2, so this runs through all 3 rows. You can note that it's different here as well. We have float type. That's due to the conversion that I have chosen. So it's not double anymore, but it's float. And it's float for all the variables. You can see here that my variable a in MATLAB, it was a matrix. Because in MATLAB, here I had that this is a matrix 3 times 4. But in C, you cannot define a matrix, but this is an array. So it's only a single line, but it has 12 elements. The same here for B. In MATLAB, I had 4 by 4, but now I have a 16 element array. And there is also one difference in how do you actually get the output value. Note here that the result in my case is stored in an array that's called C. But in the previous case, where we had just a single value, we had this as a return parameter. The reason for this is again the behavior of C, and in C you cannot return more than one number as a return value of your function. So you need to either do it like this, that you define C array and you store the results in the C array, which happens here, or we'll see next week that you could use something that's called a pointer, and then you need to pass the parameters for your array from the main function. Anyway, here we can see quite clearly that the same code in MATLAB has defined a completely different code. Now, question time.
May I have a quick interruption?
Yes.
Okay. For in my case, this one, the metric mine in case of float, it still be a double.
That's possible because you probably did not select the conversion.
Oh, okay.
It's all about the settings in the very first window.
Mm-hmm.
Here I have selected that I want to convert that to single precision.
Oh, okay.
If you have kept none, then you will have doubles.
Okay, thank you.
Other questions?
Yes, Professor. I like the compiler generated a quite different code for me for C.
Let me
Can
see.
I share? Yes.
Mm-hmm.
Maybe because I reopened the file again instead of overriding it.
That's that's right. I have used the same file, but I have overwritten the settings. So that
Okay.
might be the problem.
Okay. Can I do it? Like, can I actually correct this problem, or it's?
Well, just close this MATLAB coder window and
Okay.
run it again, and then I think it should work.
Okay, perfect. Thank you.
Okay, more questions? Great. So let's see what more we can do. So now we have learned one important property of MATLAB, and that's actually this polymorphism. So we have seen that the same code in MATLAB can lead to a different code in C. That's quite common because in MATLAB it's a high-level language, and the C code is a lower-level language, and it may be translated to for loops or while loops or whatever is necessary to create the same result. We have seen also this property. In MATLAB, you don't need to allocate the memory in advance. So in MATLAB, you just write that a equals 210, and it will automatically create the memory space for you. In C, however, you need to do this. So if I go back to my code in the compiler, then we can see that all the functions here and all the variables are predefined. So here, for example, if the code is using somewhere the variable that it has called f, then here on the beginning of my function, it's defining that f is of type float. So this allocates the space that we have in the memory. And you can see here, this is a different data type. Here they are using the type integer, and they are using it as a counter. So here they have defined the variable I, and they are using it in the loop over there, and it's sufficient to use it as an integer. Of course, if I would like to use this f as an integer, I could, but then the question is if it will be sufficient for my calculation. So here we have defined, in my case, all is float, so then here they have used the floats. Now note that also this code could definitely be made more efficient. Now the problem here is that here in the function we use the array A and array B and array C, but this array is already defined, so I could optimize this code quite easily. If you look on this part, what it's actually doing is that it's using the variable f, the float, one single number, and it's creating a copy of the array A, and it's doing the same thing here. Now if you would write a code like this as a programmer, you would most likely not copy this, but you will use directly the values that you have stored in this variable. So although MATLAB generates a functional code, as a programmer you probably would generate a more efficient one. So that's just a side note that this could definitely be optimized in terms of memory requirements and in terms of speed. Now what more can I see here? I forgot some check tags. Okay, so in MATLAB, if we are working with a matrix or with an array, we have built-in operations. If you do plus, if you do a multiply, if you do other operations with MATLAB, it will automatically be detected. So here it knows that this is a matrix and that in my function this multiplication and this addition should work with the matrix. In C, you need to create a for cycle, as we have seen in the code. So that's a difference. And also in C, you need to declare the data types in advance. So here that's what we see here in the float here. This is the declaration of the variables, and then we are using the variables in our code. In MATLAB you don't need to do that. It's done in runtime, and you can also change the size of the variable. For C, you need to declare the size in advance. So for example, if you use this command in MATLAB, well, this command generates an array of 10 zeros, of 10 zeros. So we can do it in MATLAB, but in C you need to define an array that will have a specific size, and then you need to fill it with the numbers that you want. So that's also different. Okay, so now let's see how we can use it in MATLAB. What use is this good for? So I will again go back to my MATLAB, and we will now take a look on the pop-up menu that we can call on this M file. So now if I right click, you can see here that the last menu is checking the code for code generation. So now if I run it, it will basically verify the code, and it will tell me if my code is suitable right now or if I need to change it somehow in order to compile it. In my case, it's a simple code, so there's nothing I could change in order to make it better. So now let's take a look on how we can actually use this functionality. Now what we will do is that I will give you a function, and you will use this function in MATLAB, and we will call it, we will compile it, and then we will compare how fast does it work if it's compiled or if it's not compiled. So now what you need to do is that you need to go to Moodle and take a look here on this section, and well, maybe I will just again translate the text that we have here. So this was the example that we have just done, and it was the simple addition, simple multiplication. So here you have the test files that I have just created, but you already have them, so you don't need to download them. But what you will need, well, I will hide all the others right now because we will not need them this week. We'll need them next week, and we will just need this second example, and this example will be a filter. And this kind of filter is called a moving average. So please download those two files, and this will also help me to verify if you can really access those files and if you can download them. So now please download these two files into your MATLAB folder. I will open them because I already have downloaded the files, and I will show you what's inside. One function called moje filtrace, this means my filtration, my filter, is the function that we will be compiling. So it is actually using an already built function that's in MATLAB, and this function is called filter. And the second file, this príklad filter, this means example filter, this is the test file. So I will first show you what this function is doing. Now the coefficients b and a are the coefficients of a filter. Now if you take a look on the MATLAB function filter, you will see that it's nothing else than a mathematical equation that is taking the signal and it's multiplying the signal with some coefficients. So this is the function. Y is the output signal, X is the input signal, and N is the size of the window. So this is a very simple kind of filter. It's called a moving average. And it means that it's taking the current sample, which is xn, it's adding the previous samples all the way to the history size, which they call here window size. So for example, if my window size would be 2, I would take the current sample and I would take the previous sample, and I divide that by the window size, so by the number of samples. And what this can do is that this is the simplest way how you can actually remove some noise of your signal. And that's what we will do here in my example. So in my example, I will call this function. Well, the reason why I have changed the name here is that like this I can show you how to compile this function, and then we will compare it with the non-compiled function and see the speed increase. So now let's take a look on here this example that is calling the function. So first of all, what is it doing? Here at this line 26, I'm actually calling my function, and I'm calling it on the input signal, which is x. X, by the way, is an array of samples. B and A are the filter coefficients, and Y is the output signal. And in order to call this function, I need to create my signal. So what I'm doing here is that at these 3 lines, I'm actually creating the input signal. So let's see what this is doing. Here I have just run the code, and if I plot x, then we will see that this is a sinusoidal function, and here I have this is going to be my sinusoidal function. Let's just wait when it appears. So here this is my sinusoidal function, and this is some random noise that I'm adding to that function. So it's not a pure sinusoidal, but it's a sinusoidal with some noise. And the purpose of this filter is to remove the noise, so it will be back to the sinusoidal function. So those 3 lines are generating the code for the input signal. Now this is the definition of the filter. So if you look in the documentation, you will see directly this example. Here I am using 5 samples in the history, and this creates the filter coefficients B, and this creates the filter coefficients A. Now since I'm using, let's say this is a more general filter function, I could also use different coefficients than 1 here, and we will use that next week with a different filter. Then here I'm calling my function, and then the remaining lines are just showing me the result. So we will see the input data, that's my noisy signal, and we will see the filter data, That's the output of my filter. So let's run it. Let's run the whole code. And when it's finished, we will see that this is my result. And here the blue curve, that's my input signal, the noisy data. And here this red signal is the output from the filter, so it is like a nice sinusoidal function again. So originally it was this, and then after the filter is that. Now you can see that there is a difference. The filter changes the amplitude, and it's changing a phase shift, because here we have the maximum here of the sinusoidal, and here we have the maximum few samples ahead. So by changing the filter coefficients, you may change the filter properties, which will change you the amplitude and will change you the phase shift, but it will change you also the ability of the filter to remove the noise. So now, why have we bothered at all with this example? And the reason is that now we will take this function and we will compile it, and we will see if the precompiled function will run faster. And we will actually see that it is really the case. At least on my computer, it will run about twice as fast if it's precompiled. So how to do it with the MATLAB coder? So now we have this function. This is what I will compile, and this will be my test file. So if I run the MATLAB coder, I will now select the function, which is this one. I will not use any conversion. Since I already have this project, I will overwrite it. And in the next step, we will need to define the test function. So this is my test function that I have. I will define the types. And now you can see that I am working with doubles. That B is an array of 5 elements. A is not an array, but it's just a single number. And X, that's my input signal. And in my case, it's an array of 20 elements. Now let me do the compilation. Here in this part, do not forget to press this check for issues, because at this time we will be looking for this max function over there. And what will this do is that it will create a compiled code. It will have the same name like my function, but it will be compiled, and hence it will be much faster than my original function. You may also notice that here in the background it had created for me this folder, this CodeGen folder, and we will find the compiled version of my function in this folder, and we will use it in a few minutes. Okay, we can compile it again in C. We'll just see what is the code looking like. And what will this do is that it will be, let's say, a more complicated function. You can see here that it's quite long, but we can understand what is it doing. This is my function. This is where I call the filter. we can see that here I have the input parameters. This is the input signal, and this is the output signal. The main filter, the filter algorithm is this. So we can see that it's a loop of 2-4 cycles, and actually the filtering algorithm is only this line. Here, this is some coefficient times the sample, and this 4 cycle, it's the history. So because in my filter I have used 5 elements in the history, so that for this reason here this is running up to 5. So this is the filter itself. Now this line is allocating the memory for the variable y, and here is how large should it be. And for example, this side, this part of the code, this is checking if the numbers are really numbers. So because in C, if you do some calculation, this check is not done automatically. But in MATLAB, it may happen that for some reason you have the values in the array is defined not as a number, but the filter needs to work with a number. So this will do the check, and if it sees that it's not defined correctly, it will define that here we will have some specific value of the coefficient. In this case, it's defining that as 1 as the value of A of the inputs. So if I now go back to MATLAB, if I have finished that compilation, what we can do is that we can verify how long does it actually take if we call this filter compiled or not compiled. So in MATLAB, it's easy to do, because in MATLAB we have this tick and tock function. So let's try this. Here I will call the tick function, which starts a timer. Then I will call the filter, and then this tock function finishes the counting and displays how long did it take to make this function between this tick and tock events. So now on my computer you can see that it takes about 8.4 milliseconds to do this function. Now what we will do is that we will compare it with the compiled version. And for this you need to go into the CodeGen folder, and in the Max folder you see here, this is my project name. It's the same like the name for the function, and here I have this file. This is the same name, _MEX, and this is the compiled version. So now I will just copy it to my main folder in MATLAB like that, and it's in there, and I can call it in my code. So here in my code I will just now uncomment this timing, and those 3 lines will time the function that is not compiled, and those 3 lines will time the function that is compiled. It will use exactly the same parameters, exactly the same inputs and outputs, but we will see what is the difference. So let's see how fast it can run. Okay, let's run it again. For some reason that I don't know why, if you run it for the first time, then the compiled version is longer. The reason is probably that it needs to run to read the file into the memory from the hard drive. But if you then run it next time, then you can see that it's very strange right now. Maybe the problem is that I'm recording the lecture video right now, but at least well, I hope on your computers it's will give you the faster result for the compile function. As I said, on my computer I'm just recording this screen into a video, and that might cause me some trouble. So were you able to get a similar result on your computers?
Yes.
Kind of.
Okay. And can someone show me the screen and so that we can compare the timing? Okay, I see. So we have a similar result that for some reason you well, run it again and see if the compiled version runs faster.
So by running it, you mean take the again the code?
Yeah, but now I see that your code is not correct.
Oh,
because it needs to be like this. You have commented this this line. No, this line, but you need to tick and talk around this line, and then another tick and talk around the compiled line.
Oh, okay, got it.
I will just see if that's not my problem, but doesn't look like it. Let me just run the code again on my computer. Okay, now for some reason, now I have the correct result already, but let's see if this will be your case as well. Yes, this is correct. So that now just run it. Yeah, I don't know what's the problem.
Slight difference. Okay.
Slight difference, but the correct result that we are expecting looks like this, and this is the compiled version, and this is the not compiled version. So this was the result that I was expecting, that the compiled version is much faster than the non-compiled version. But the problem might be that your computer is doing something else, mine as well, and this is not running in real time. So maybe some other process in the computer was doing something and it interrupted the algorithm in MATLAB.
Maybe because I'm running multiple stuff at the same time. Okay.
Yes, that's maybe the reason. So next time we will learn how to run the code in MATLAB and how to run it in Simulink. And in a few weeks we'll learn how to run it in real time, so that this has the highest priority and it's not interrupted even by Windows. Okay, so what we will need until next week. So until next week, you will need the development board. So please let Mr. Hiski know who wants to have it. We'll order it as soon as possible. And you will also need to download software for the board, and the software is called STM32Cube. So please download it. It's quite large, and install it. And I will just briefly show you how it looks like, and we will use next time. So here is the software when it's installed. It has about 600 megabytes when you install it, but then you need the compiler for the CPU, which is another, I think, 1.2 gigabytes. So it's quite large in total. So when you install this this environment, then launch it, and in the wizard that will appear in a few seconds, you can do it even before you have the board, and you need to do it because it will download all the packages that you need for compiling the project. So I will just show you what I have in mind. Just give me a second before it opens. And if you just create an empty project and you run it with the correct CPU, it will simply download all the required files. In order to download it, you need to create a free account on this web page. So download this STM-Cube. It's somewhere on this web page. There is a download button, and you can download it. If you launch it for the first time, it will show you this wizard, and the board has a CPU that is called 767ZI, and like this you can select it. And now if you just select this line with the CPU and hit next, now in my case it will already propose me the project name. In your case, if you enter the project name, for example like a test, then the next step is that it will download all the necessary components, which will take, I don't know, depending on your connection, may take 10 minutes, may take 1 hour. So that's the reason why I show it to you today, so that you have this software ready for next week. Do you have any questions?
No, thank you.
Okay, so if there are no questions, then we'll meet next week on Wednesday. If you have any questions during the week, then let me know by email, and will try to answer them.